Yes, how are we, guys? I'm just going to have a quick rundown on motion, just particularly going through your speed time graphs, how to analyze them, how to calculate the distance under the curve, and literally just how to answer general questions on motion. So this just past paper insets from 2024, 2023, respectively. So you guys can equally also just go through your 2022 and 2021. All right. So the first question that we have here is to just circle vector quantities. So questions like this can come in where they might ask you to circle vector quantities. Please be careful with the command word. Hey, sometimes they might say no. You need to. They might say though you need to underline. So then you must underline. But in this case, we are only expected to circle, which is exactly what we are doing here. All right. So what are the vector quantities that we have here? So the vector quantities provided here are your acceleration, and that's acceleration and the velocity. The rest are scalar quantities. I mean, no way mass, speed, and time can have direction. Then when you come over to your speed time graph, this is where I want you to pay attention if you do come across a speed time graph. So the first thing you always want to take a look at is look at the heading in terms of what they tell you. So here you are told figure 1.1 shows the speed time graph for a train traveling from station A to station B in particular. And what you're provided with is a speed time graph. Now, it's always important. The first thing you want to look at is really reading your scale. You must have the ability to read your scale, the difference in the scale. Because if you can't read your scales, both the x-axis and the y-axis, it becomes a challenge for you to actually know what the actual values are. Then you get to the actual questions where you just literally now need to read and answer. Questions that ask you to state are straightforward. For a command word that simply says state, which means just state. Obviously, based on the information provided, state the maximum speed of the train. Now, to do this, you have to take a look at the highest speed it ever got to. And the best way is you take a ruler, and that should be the highest speed here, and then you literally just interpolate so that you can see exactly where that is. And if you read off your scale, that would be 51, 52, 53, 54, 55, 56. So it's 56, and pay attention to the unit as well, because by the time you write your answer, you need that 56 accompanied by the unit. So don't leave the unit out. It's important to have your units. All right, then comes the regular questions, right? Here, the command word is to describe. So I look at the command word and I look at the number of marks. So that means my description should be worth 2 marks. So then they told me describe the motion of the train between station A and station B, which means from where it came from to where it went. Now, gradually here you could see that the train here was moving, and you could see this slope is very steep. It's not constant. And because the slope here is very steep, you could see that it's actually accelerating or moving with increasing speed. And then when it actually got to 100 seconds, it started moving off with constant speed. And you could see because the line was having a gradient of 0. So that means there was no increase. So it's constant. And then eventually it moves off with decreasing speed or decelerating. So you'd see here in my explanation, that would be the train is moving with increasing speed. That is true for this. Then with a constant speed, that is when the line here became constant. And then thereafter, it starts to decelerate. So this is worth 2 marks because I mentioned two to three things. So it's very important that you look at the command word, you look at what you need to describe. And just be careful generally. Go through your notes there where we describe speed time graphs and how they look like. This is also going to be very important for paper 2 multiple choice, when you need to know how to describe and how to find that. And you can literally see how what I do to the graph. Here I will highlight, I will interpolate, just so that I can know what I'm dealing with. Right, then we proceed over to what we call every time, and this is very important. If you are given a speed time graph and they ask you to calculate the distance, always know that you are going to use the area under the curve. Now, the markers want to see the statement that states the following: that area under the curve equals to the distance. You need to state this. So which means whatever area I have under the curve equals to the distance. This here is worth 1 mark. The moment you state that, it's going to be worth 1 mark. Now it's important. The areas you're going to get under the curve would be areas of a triangle. So you need to know that by heart. Area of a rectangle, depending on the shape, and then area of a trapezium, where you are dealing with your sum of 2 parallel sides multiplied by the height. So, or you can sometimes just basically combine all the shapes together. So in this case, they're asking for the overall area under the curve. So what do we do, guys? We go on to our speed time graph. And literally what you will see here on the speed time graph is the following. Like I said before, now you can interpolate, you can show so that you can just know. Now the parallel sides will be the sides that are actually parallel to one another. So that would be this side from here to there, and from 0 all the way to there. These two sides are parallel to one another, which means that's going to be your A plus B, right? Why am I saying it's going to be your A plus B? Because this whole shape here is a trapezium. And remember, now you can get 2 trapeziums. You can get an isosceles trapezium where the 2 sides seem to be equal, or you can get a trapezium that looks like that. So whichever way, that's a trapezium. And the height of the trapezium is basically the distance from here all the way down. That's the height. So on this graph, I just need 3 things, really. What are those things? 3 things. I need the sum of the 2 parallel sides, and I need the height. The height would then be this distance here, which you can always get on this side. And clearly, the height of this thing is actually 56. Then one of the sides, as you can read through here, you can see what I did here to find A. I just drew lines going all the way down, so I can actually just identify where exactly it stops. And you see here, it's at 80. So it starts at 80 and it stops at 480, which means when I get the difference between the two, I will get the distance from here to there, which is going to be 400. Because if I take away 80 from 480, I get 400. Then this one from here to there is very clear, the bottom one, because then the scale is readable. So you've got 500, 510, 520, 530. Right? So then we go to calculate our distance. So we said before, area under the curve, and then we indicate it as such: 400 plus 4 plus 530 multiplied by the height, as you could see. And obviously, you want to keep your answer exact to 2 significant figures, please. And the unit. So you'll get 1, 2, 3. So there's a method mark here as well, because then you take a look at your calculation. Not this one, but no method mark, but rather the mark here went to the first part, which is showing that area under the curve is equals to the distance, and then 1 mark for the correct answer, 1 mark for the unit, which is why you get 3 here. All right, then generally what follows after that is that they would ask you typical questions like, why was the journey longer? What made it longer? Then your knowledge of forces must also come into play. And just generally to understand that as well, just the formula of speed equals the distance over time, so that you can take a look at what happens if the speed decreases, what happens to the time? If the time decreases, what happens to that? So just understanding that knowledge. So they told you on a different day, the train takes 650 seconds to travel between station A and station B. Suggest one change to the motion of the train that leads to a longer journey. I mean, it's the same journey, but on a different day, it takes longer, as opposed to the 530 seconds it took at first. Now, if I look at this graph, there's only one way it could possibly also take longer. If it was traveling at the longer constant speed, then it will take long for it to go there. Or if perhaps it was moving at a slow speed, then maybe, or lower acceleration, then that can also be the case. So here you could have said it's moving probably at a lower acceleration. That's why it was taking longer. It was taking time to accelerate from the beginning. Or maybe the train was moving at a longer constant speed, which means for the longest time it was probably just traveling at the same speed, which is why it took longer. So generally, these are questions that you can get in your paper 4. Okay, then moving on to another question. This one now refers to your forces. So it's very, very important that you understand your forces, particularly the term resultant force. A resultant force is applied to an object with a velocity v in a straight line. State two different changes to the motion that the resultant force may cause. Now, the question was just asking about what changes can a force actually make to an object. So if what state two different changes to the motion, they are referring to the motion a resultant force can do. So number one, it can change the magnitude or size of the velocity changes, or the speed changes, because it's like you take a ball and you apply another force, the speed can change, or the direction can also change. So that's when they are making reference to the motion, not any other thing. Motion, not the size of the object, but to the motion. So the velocity can change, or the speed changes, or the direction changes. Then here they're asking you state one other way that forces may change a stationary object. And they're saying a stationary object, which means every emphasis is on a stationary object. They can change the size or the shape of the object, right? If you apply a force. Now here they were asking, and these questions are becoming quite common, I should say, where they ask at least one simple way in which you describe an experiment. I would actually encourage you to watch those short videos, not all of them, just browse through at least for 15 minutes, just so that you can have knowledge of how to plan a basic experiment. Yeah, they will just ask you either one of those ones. You don't need to study them in detail, just browse through. So this one, they were just asking something about the uniform ruler, which is at a pivot, and a selection of masses. So you take a look at what you are given. So they gave you a uniform ruler. The word uniform means a constant ruler, a pivot, and a selection of masses. A selection of masses can be used, which means they're already telling you can use different masses. Can be used to demonstrate that there is no resultant moment on an object in equilibrium. They just wanted you to show how you can actually come up with an experiment to indicate that it's actually in equilibrium. So, and I told you with an aid of a diagram. So you could see here, I put the masses here already. That's a mass. And that's a mass. And that's the pivot, because they told you that you have a pivot with different masses. And if it's in equilibrium, then that simply means your clockwise and anti-clockwise moments are the same. This is obviously going to be clockwise, and this will be anti-clockwise. All right. So here now, they are telling us to plan the experiment. So what are we going to do? We're going to place the center of the meter rule on the pivot, as you can see here, and then add masses on both ends at the same time. So that, why are we putting it at the same time? So that we can find the balance already. Then here we are saying add masses on both ends, or on one end, like what we said there, and then find the moments, because we need to find the moments. And a moment is force multiplied by the perpendicular distance. Then we must state that the sum of clockwise moments is actually equals to the sum of anti-clockwise moments. Then we prove that that particular object is actually in equilibrium. All right. Then here, I always tell you as students, before you answer the question, study the figure. See what the figure is telling you. So that you're told figure 3.1 shows a side view part of a concrete track at a skateboard park. And you are given points A, point B, point C. Then we said, when an object is placed at a height, it possesses what we call gravitational potential energy. Now, here we are told the skateboarder is initially at rest at point A, which means at this point is not moving. The skateboarder then travels through point B and comes to rest again at point C. So you are told exactly what's happening. Then they told you describe the transfer of energy, which means how is the energy being transferred as the skateboarder travels from A, B, C along the concrete track. And you can see here from A, that's gravitational potential because you are placed at a certain height. That gravitational potential is then going to be converted into kinetic. And from kinetic, because you're going to go back to rest, it goes back to gravitational potential, which means literally in your description, you have to say that is just gravitational potential energy to kinetic and back to gravitational potential energy again. All right. Then moving on, here you are told B is at the ground level. And you could see on the diagram that B is at the ground level. B is here. This is where B is. So B is at the ground level. Then you are told C is at the height. That's where C is placed in terms of the height. Above the ground. The mass of the skateboarder is this. Now you would have seen here that already I highlighted. This is my height. So I know I have height and I have M. The reason for that is I'm already writing out my quantity so that I can figure out by the time they ask me to calculate what I need to calculate and what I don't have. So here they're asking you calculate the work done on the skateboarder as she travels from B to C. Now here they're asking for work done. This literally work done's formula is force times distance. And I said before, guys, energy is just one thing. So work done is the same as gravitational potential, and it's equally the same as kinetic energy. So even if one of them is not given, these things are just the same because energy is just being transferred. So here I have to ask myself, okay, I don't have the force in the problem that I'm given. Okay. And I know that force can be calculated as what? Mass times gravity. So I can literally take this mass and I must make sure it's in kg multiplied by gravity's constant, which is 9.8. And I get my answer for the force. So I can do that and I can plug that into that formula to get the force. Do I know the distance? Yes, the distance is the height. So I can calculate it like that. Oh, I can just do it straightforward using gravitational potential because work done and gravitational potential are the same. Since I'm given M, H, and G is a given constant and gravitational potential energy's formula is mgh, then I'll just take that 65 multiplied by 9.2 multiplied by 2.8, then I'll get an answer of 1,783, which I must then round off exact to two significant figures to get 1,800, and I must not leave my unit, which is energy, in joules. All right. And here you are told to do the following, the second in the other question. You are being told the skateboarder falls off the skateboard at B. So at this stage here, they fell. Which means if something falls now, guys, when something falls, there will be contact. And if there's contact in physics, we refer to that as collisions. So that is what we refer to as collision because the things collided. The person collided with the ground. So there is collision. So which means there will be a change in momentum. But a change in momentum that is short is what we refer to as the impulse. So here we are told she hits the track and comes to rest. And when something comes to rest, what are we referring to, guys? We refer to the fact that the final velocity becomes zero. That's why you can see I already wrote V equals to zero. The skateboarder falls off the skateboard at B. She hits the track and comes to rest after a few milliseconds. And the word milli, guys, just for context, if you come to it, milli basically means times 10 to the power of minus 3. So if somebody gives you a unit seconds in milliseconds, then you must just replace the word milli by 10 to the power of minus 3. Here they are telling you now, state the equation that defines the force with which the skateboarder hits the track. That will be the impulse. Because it's impulse, and impulse is basically Ft equals to the change in momentum. We will then make the force the subject of the formula because the contact was very short. So that's literally just what we are referring to. So we will divide both sides here then by T. And then we will end up with F equals to M delta Vt. And this is how you would go about that. All right. Then you might be given speed time graphs that have got curves. And here, this is where your knowledge of tangents is very important. Because to draw a tangent, you can't find the gradient of a curve unless if you draw a tangent. So here you are told the following. You are told the speed time graph for an ice skater. And you could see here, this is the speed time graph. And the first thing I always do is I take a look at knowing how to read my scale. Because if I don't know how to read the scale, whatever question they're going to ask me, I might not be able to answer. So the speed time graph. So let's go to the questions. And then they ask me, describe the motion of the skater between T0 and T3. And T0 is here, which means time T0 and time T3. And clearly time T0 and time T3 is the one that creates this rectangle here, as you could see. Then here they say, all right, calculate the distance traveled by the skater between T equals to 0 and T equals to 3 seconds. Okay, but here the first question was just describe the motion on skateboard. Between that, the motion here you can see it's constant. It does not change. You are following the graph, so the motion is constant. So the correct answer here would be constant speed or no acceleration because the velocity is not changing. Then again, they said calculate the distance traveled, and I know it's a speed time graph. The first statement I need to write is the area under the curve equals to the distance. And they were specific here because I was told between T0 and T3, which means it's between these two intervals, which gives me a right angle triangle, which means the one side is 3 and the one side stops here at 11. So that will be 3 times 11, which will give us 33 meters. So very important to know that. Then here they are asking you, state what is meant by by deceleration. Deceleration is just literally negative acceleration because it's when something literally slows down. So that's what we refer to as your deceleration or literally decreasing speed. Then here they tell you now, draw a tangent, and they will tell you the point. Draw a tangent at t equals to 9 seconds. That means we go, because we are given a curve, we can't calculate the speed here unless if we draw. And if you see here, t equals to 9 would be this here. So the tangent that they want us to draw must come at that point. And you can see my tangent, I extrapolate it. And then the reason why we are drawing a tangent is because we are looking for a straight line to calculate our rise and run, which will be the change in the x and y, which means I must know what the values are here. The values are here, and what the values are here, and what the values are here and there. So this will give me this, which is going to be my x, and this is going to be my y. And then once identifying these points here, you could see here I identified those ones. It will be our change in y over our change in x, which is the highest y would be here. And you can see here the point that I took is 3.6. And it starts at y0 because at this particular point y is 0. And you can see here x is somewhere there. And the other x point I chose was somewhere there. So I need to subtract this x point from that to get the difference, which is what we did here. We took the 6 and we minus it with the negative 11.4. Now, the tangent that we got there is negative, obviously, because the gradient we got is negative because it is decelerating, it's slowing down. And that's how we calculate some of those things. And obviously, it's deceleration, so your unit must be meters per second squared. So units, even a unit, guys, will give you marks. Don't leave the units out. You won't get a mark for the formula, but you will definitely get a mark for the unit if the unit is not given. All right, so that is it for the tangent. This one was now the tricky one that was actually written recently in 2025, May, June, where we are dealing with moments. And moments, the most important thing, guys, is sometimes they can trick you. They can even give you moments or forces that are like going on top. You must just know that if I've got a force going in the opposite direction, these two forces must balance each other out, right? And simply this one plus this one will cancel out this one plus this one. So that information is also equally important. Now, in this particular one, and we did it in class at one point, it was quite tricky. It was quite tricky to solve, but again, we're going to go through it just so that we all understand what needs to be done. Now, with moments, you must just please understand that clockwise moments equals to your anti-clockwise moments as well. If the body is said to be in equilibrium. All right, so let's start off this together. So we are told a beam shows a balance. This shows a balanced uniform meter rule made of wood. And they give you numbers across the board. It's wood, I can see it's a rectangular thing, which means it's a cuboid. And I've got my masses, and all of them have got forces here. You could see sometimes they might even ask you to find the mass. And you must just know that force equals to mass times gravity. So if I know the force, I can get the mass. So for this one, they're asking you, the width of the meter rule is 2.6 times 10 to the power of minus 2. And the thickness, how thick it is 6.0 times 10 to the power of minus 3. Then we are asked to define moment of a force. Please go through that book that I gave you to know your definitions. Moment of a force is just the force multiplied by the perpendicular distance from a pivot. Now, here they're asking you, on figure 2.1, mark the position of the center of gravity of the ruler with a point X. Label the point X from the 0 centimeter end of the ruler. So 0 centimeter end of the ruler is from here. Now, the point X that we are referring to, guys, is the point at which most of the mass is actually concentrated. Is the point at which most of the mass is actually concentrated. And it's basically like midway through the diagram. So at this particular junction, you could see here we've got 0, 10, 42. And then here we come from 100 all the way down. The difference is there. Then they said we must mark off the pivot point. So the pivot point will be somewhere here. All right. Then we proceed. Show that the mass of the meter rule is 0.081 kilograms. Now, to show that this is actually going to be 0.08 kilograms, 0.81 kilograms, we were told from the beginning that it is balanced, which means we need to state the sentence already. However, we need to see how many moments are on our anti-clockwise side and how many moments are on our clockwise side. If I look at this now, you can clearly see in this particular diagram that I've got this moment acting here, which is acting from the pivot point now. That will basically be the difference of 10 and 42, which will just literally be a distance of 32 from the pivot point. And then on the other side, I've got this here, which is also acting. Now remember where the pivot point is. The pivot point is here. Because the pivot point is there, even the weight of the ruler is a moment, which means on this side, I've got 1, 2 moments. So I have 2 moments for my clockwise, hence why we said F1 multiplied by D1 equals to F2 multiplied by D2 plus F3 multiplied by D3. Now, the only way to show that the meter ruler's mass is this is we need to figure out what is the weight of the meter rule. What is the weight of the meter rule? Which means what is the force of this meter ruler, which is the one here now, which is the one here. We want to figure out what the weight is. What is that particular weight? We want to figure that out. And unless if we know that, we will not know anything. So we already know, okay, the weight of the ruler is acting and is acting downwards. And we are told already in the beginning that we have this weight and this weight acting there. So we take that now, slightly fast while explaining this because we went through it in class. Hope you do understand. So then we know, okay, the weight of the meter rule from the pivot is there because that's where it's acting, is literally 8 meters away. Because why are we putting it here, guys? Why are you putting the weight here? Because it must be at the 50 centimeter mark. That's where most of the weight is going to be concentrated. That's why this is acting down here. Because the ruler is most 100. So where is most of the weight going to be acting? It was at the center at 50. That's why we put the weight there. And from the pivot point, the weight is only 8 centimeters away. If you subtract that from the other, because from here to there, you've got 38. And then obviously, if I was to minus 42 from 50, I'll get 8. So I know the distances. The first distance on the other side is now going to be 32 multiplied by the force, which is going to give me this moment. And you can sort of calculate the moment separately, not just putting them into one formula. And I don't need to convert this into meters, so you just keep it in centimeters. And then it's going to be equal to the sum of clockwise moments, which is now going to be the moment of the ruler, which is now force 2, which we don't know, multiplied by the distance. And then we take force 3, which is this force here, multiplied by the distance it is away from the pivot point. Then you'd see this side, we get 10.88. And here F2 multiplied by 8, I'll get 8F2 plus now here 0.12 multiplied by 38, I'll get 4.56. Collect your like terms, which means now subtract 4.56 on both ends. You'll end up with 6.32 on this end, and then only 8F2 here on this end. Then you must divide both sides by 8, as you can see. And then we end up with a force of 0.79. But this is not the final answer because they said we must show that the mass is that. So because I know what the force is now, and I know that force equals to mass times gravity, I can just make m the subject of the formula. Then I'll take my answer here, which is 0.79, divided by gravity, which is a constant given in exam already. Then you can see that I'll get 0.806, which is approximately 0.81. So quite fairly simple. And it's something that you are expected to know. Now, suppose maybe you didn't get this right in the first place, but then they ask you again and they continue and giving you another chance to redeem yourself to get 2 marks. Then here they are telling you calculate the density of the wood. Immediately then density's formula is rho equals to m over v. And then I was already given the mass even without me calculating it. So I can calculate that, which is going to be 0.081. But then I've got a problem. I don't know the volume, but I know that they said it's a ruler, and that ruler looks like a cuboid, which is actually length times width times the height. Now I go back here on the information given, and I take a look at what am I given. So in this instance, you can clearly see that I was told that the length of this entire ruler is literally 100. So you know that the length is 100. The width is 2.6 times 10 to the power of minus 2 meters. And this is also in meters. So I have a problem. The values I need to use are these three to get the volume. But one of them is actually in centimeters. What must I do? Now I need to convert all of them into meters. So I need to take this one here and I just literally need to convert it into meters. So I need to divide it by 100, which just becomes 1. So then I will have the three values now. It's going to be 6.0 times 10 to the power of minus 3, 2.6 times 10 to the power of minus 2, multiplied by 1 to give me this volume. Now that I have my volume, I can plug it into the formula. Then I get my answer exact to two significant figures with the unit to then get my 2 marks. So that's literally or generally what you're supposed to do for that one in order for you to get the answer. Let me come to the part that many people don't enjoy as much, but I do really. Momentum is just awesome, guys. So defining momentum, you can just define momentum by the formula by saying momentum is equal to the mass multiplied by the velocity. And in this case, pay attention to the diagram. When they tell you the body is stationary, the bodies are moving. And remember, if the bodies were moving in opposite directions and they were collided together, then they were not moving in the same direction. One of the velocities has to be negative if they were not moving in the same direction. And if the one body was stationary and the other one collided into the other one, then you expect that body, then they tell you to stick together, then the masses will combine. If they don't stick together, then obviously each one of them is going to move off with its own velocity. All right, so with that said, we now have our A and B on the track. So let's move on. So you are told train A is here, train B is there. I look at the diagram, I study it. And I look at what I'm given. The mass of train A is 0.45. So I already mark it off as my M1. The mass of train B is 0.21. So I already know it. The trains don't have motors, right? I'm told. They don't have motors. So they're literally just probably moving on their own. There is no driving motor in the train. They're not powered by a motor. A train A travels towards train B. They collide. So you are told they collide, which means this is already a principle of conservation of momentum. Immediately before collision, pay attention to the terminology. Before they have collided, the velocity of train A is, so that means that's the initial, that's before they've collided. And it was moving to the right, which means where, guys? To that side. And the velocity of train B is 0.12 to the left. So here they move. This one was moving to the left. These velocities are not moving in the same direction. So the one moving at the left, you can just make it negative already. So it's different directions, so this one becomes negative. Then you are told they stick together. By the time they tell you they stick together, so that means after collision now, the masses will combine and you do expect them to move off only with one velocity. So I took the momentum now of M1, the momentum of train 1 is going to be M1, U1, momentum of train 2, M2, U2. And they said calculate the velocity of the train. So we come up with that formula. But you would see now, because they were not moving in the same direction before collision, one of the velocities definitely need to be negative. Then I continue. And you could see here, I plug in the values and I add them together here. And you could see here is just the mass and the velocity before collision, the mass of train B and the velocity before collision that we said we need to make negative because it's moving in the opposite direction. Equals to after they stick together, we combine the masses, we add the masses. Now they only want us to figure out what the final velocity is. Solve this, you end up with 0.66 V. And then here now you're going to compute this. You're going to end up with 0.153. This now becomes negative, you subtract. Then you can see now you've got this on this side. You want to solve V, you divide both sides by 0.66. And this cancels out. And then you end up with your answer. And you can see here, the answer we got is a positive. Because it's a positive, it will move to the right. If it was negative, the velocity will move to the left. Even just by saying that's a mark, that's 1 mark here, 1 mark for the unit, 1 mark for the method. Right, that's how you get the 4 marks there. So pay attention to some questions that come like that, and then just know how to do it. Every time you deal with momentum, when they're asking you to find the average resultant force, two formulas that you can really always use all the time with resultant force is your F equals to ma, where your a, you know, is your acceleration, provided if you know your initial or final velocity, then you plug and play. Or for momentum, you can just use the formula for impulse, which is m delta v over t. Now, just m delta v. And then if you make F the substitute of the formula, it becomes now m delta v divided by t. Now remember, please, delta v is literally just your change in speed. And this whole thing here literally just stands for change in momentum. So here they're asking you, a different train is traveling with the momentum, which means that's the momentum of the train. That's the change in momentum, delta p. The train slows down and stops after 2.1 seconds. Calculate the average force. Now I have the momentum and I have this. I can't use this because I don't know what the acceleration is. So definitely I can just use this formula where I have the change in momentum already and the time. I divide that, then I get my answer. 1 mark for the correct answer, 1 mark for the unit. So it's very, very important. And again, correct answer exact to two significant figures unless stated otherwise. All right. Another speed time graph here. So we are told a car travels at a speed of 20 meters per second. The driver applies the brakes. When somebody applies the brakes, you expect them to come to what? Rest. So you expect their final velocity to become 0. So clearly now I study the diagram. I take a look at how to read my scale so that I just know exactly how my scale is reading. So I know how to read all the other values. Then here I'm told that that's the speed time graph. So let's answer the questions. This is very direct. Determine the speed of the car at t equals to 2 seconds. So I go 2 seconds. I interpolate like so, right? I take like my dash lines, interpolate up until I hit that. That's 2 seconds. Then I take a look at how it's corresponding on the other side because they asked me about the speed. And I read. I know that this is reading in fives. So that will be 10, 11, 12, 13, 14. In between 11 and 12, that's just going to be 11.5. So my answer therefore here becomes 11.5. It's a reading. So please, when you are reading something off, you don't need to write it to two significant figures because it's something that you are reading off. So you write it as is. All right. Then you proceed off to, again, calculate. Here they are telling you calculate the distance traveled by the car between time t0 and time t4 seconds. How do you do this? Again, it's distance under a speed time graph. So you need to show area under the curve equals to the distance. Area under the curve equals to the distance. So this gives you 1 mark already. Then I go and I look at, man, what type of shape is this? Now, sometimes the students, we can be extra, and then you guys might decide, no, I'm just going to do this, first calculate this. That's still fine. And then later, you would calculate the area of the whole entire triangle. And then you add the two areas together. That's still fine. But definitely, I can see this whole shape is a trapezium, right? But the irregular trapezium, not the isosceles trapezium. So this one is literally this one that looks like that. So if that's the one, I need to identify the sum of my two parallel sides and my height. My height is clearly 20 already. And I must just take a look at where this one starts. It starts at 0, and it's in between 0 and 1. So that's going to be 0.5. And then this one goes all the way up until 4. So my A becomes 0.5. My B is 4. My height is 20. So I can plug and play. So that's going to be A 0.5 plus 4 multiplied by 20, because that's my height. I get my answer is 45 meters. Quite simple, guys. It's extremely simple. Then here they're asking you to calculate deceleration, and calculating deceleration is as easy as you using the formula for acceleration, which is A equals to V minus U over T. And literally, they told you at time T equals to 0.5 and 0.4. So that means I must find the deceleration. And I must actually see if on the graph it is decelerating also. You can clearly see that it started decelerating after 0.5 seconds. You see that? Because this whole line is going down, so it's decelerating. So now they're asking us to find that deceleration. How long did it take is the question. It started at 0.5 and 4. So that would be the difference between the two to give me my time. And therefore, my time becomes 3.5. What was the initial velocity? The initial velocity was 20. The final, it will come to 0 because it's decelerating now here. So from here to there, initial was first 20, and then it decelerated all the way to 0. So since I have my V is 0, I'll plug in V is 0, and then my initial is 20, divided 2, I will get a negative answer, which is an indication that I actually calculated the deceleration. But magnitude is never negative, so I can leave my answer as A, positive, which then gives me 5.7 meters per second squared. So quite important, guys, to do that. Then generally here, we have the following. Figure 2.1 shows a space vehicle which consists of a capsule and a nose cone. So here's a capsule, here's the nose cone, and I'm told the space vehicle is moving at a velocity of 7,800 meters per second. So I have the speed. The mass of the space vehicle is 840, which I assume is the whole thing. Then you could see I'm given an arrow, okay, indicating the speed is going that side. Then I'm told here in the beginning, show that the momentum of the space vehicle is approximately 6.5 times 10 to the power of 6 kilograms meters per second. So I'm told what the mass was, and I know it's 840, and I'm told what the speed was. So with the 2, I can calculate the momentum. So momentum equals to, which is lowercase p, m for mass, v, and then you multiply the 2 to get 6,552,000, which if you write in standard form, it will be 6.55 times 10 to the power of 6 kilograms meters per second. Then here I'm told the capsule ejects the nose cone, which means now the nose cone is ejected, and I'm given arrows. The velocity of this side is moving that side, and the velocity of that one is moving that side. So arrows are facing in the same direction, which means none of the velocities after collision now in this case are going to be negative because they are going in the same direction. So here they are telling me now, determine the velocity of the capsule after the nose cone is injected. We already know what the momentum before was. It was that 6,552,000. Now we've got to take a look at what's the momentum after, because there was some form of collision here. Separation is still called collision. It's like recoil. Then now you can see after they have collided, after they have ejected, this one's going to move over with its own velocity and its own mass. This one also has got its own velocity and its own mass. But now they want us to figure out what the velocity of this one is after. So we plug and play. So we have the velocity of the capsule, which is, the mass of the capsule, which is, so this is supposed to be 720, né? So not 750, 720 multiplied by that to give us 720 V. And then here it would be this one now, this one's velocity multiplied by this one's mass. to give us 942,000. Then obviously I subtract both sides by 942,000. This side I'm going to be left with 5,610,000. And there I've got 720. So here I did it the right way. Then we divide both sides by 720 to end up with 7,791. And they told us to leave the answer to three significant figures, which is why we left it at 7790 meters per second. All right. So quite important to just know how to deal with any of those questions. Pay attention to what you are given. Try and just literally take a pencil and highlight and take a look at or mark off what I'm giving so that you can take a look at what formula to use. Then we are told the different space capsule returns to Earth. Figure 2.3 shows the capsule just before it lands in the sea. The capsule travels at terminal velocity. Terminal velocity is when the air resistance and the weight balance out, right? Then now we are told in this case, this is why you can see here, force equals to the weight. You can just know that force and weight are the same. Here I'm told the upward vertical force acting on the capsule, which means here is this capsule here, there's an upward force acting there, is 120 kilonewtons. The word kilo means 1,000, so we must just multiply that. Remove the prefix, that will be 120 times 10 to the power of 3 newtons. Remember to always convert your prefixes, very important. Calculate the mass of the capsule. The mass of this capsule, how are we going to calculate it if all we have is the force? Then we know, most guys, I said weight and force are the same, which is why force is also going to be equals to mass times gravity. So in that formula, we now need to make force the subject of the formula. We need to make force the subject of the formula. So the formula is like so. Give me for my mass. So here, you see that M equals to force divided by gravity. And our force is 120 times 10 to the power of 3 because we need to remove the kilonewtons, divided by gravity, which is a constant. We get 12,244, which if we round off exact to two significant figures, always, guys, so together with the unit, I'll get 12,000 kilograms. Very straightforward and very easy. This one in class as well, when we're doing it, I now said it's important, guys. Look at the diagram. See what's happening. Anything that stretches will always give me what type of energy? Elastic potential energy. So this part where this boy seems to be shooting the arrow towards the target, that's elastic potential energy. So here I have shows an archer aiming an arrow at the target. Soon as you release this thing, its elastic gravitational potential energy is going to change into what? Kinetic. Already, I know what this is all about. Then I know this thing is, if it's moving here, there is air. Air can become what? A resistive. There will be air resistance, which might oppose this arrow from moving as fast as it actually must. That's why it's there. Then I study it already. Then I go and I start answering the questions. Then they say the archer pulls back the bowstring, doing a total work done. Now, work done is just energy transferred. Work done is the same as gravitational potential. It's the same as kinetic because that energy that the work you are putting in can be converted into kinetic energy. Then you are told her hand moves a distance of 0.45. That's now her hand doing the work. The bow is bent, and you can see, and stores energy, which you already know is elastic potential energy. Then they tell you here, show that the average force applied by the archer is pulling the string back. How are you going to show that the average force is actually applying this? Now I'm asking myself, man, in this problem, I'm told that this is the work done. This is the distance. Work done, distance. What's the formula for work done again? Work done equals to force times distance. Oh, which means they want me to find the force. So I make the force the subject of the formula, which will become the work done divided by the distance. I check my units, joules, not kilojoules, good. I have my distance, good, meters. I divide and I end up with 244, which I then round off to two significant figures to be 240. Very, very important to do things like this. Then we said now, the archer releases the bowstring and all the energy is transferred to the arrow, which means when the work done or the elastic potential energy is released, it's being converted into kinetic. Now they're going to ask you must to obviously calculate, not necessarily calculate the kinetic energy, but calculate something else. Because if you already know the work done is already equal to the kinetic energy. The mass of the arrow is 0.0030 kg. So I know that's the mass. I'm given the mass. Then they say calculate the initial speed. I can't use this formula because I don't have the time. So that's out of the equation. But they said kinetic energy, which means, okay, let me write down the formula for kinetic energy. So they're talking about kinetic energy, so you must already see what they're trying to talk about. Then I say, okay, kinetic energy I'm given because I already know what the actual work done is. And I said kinetic energy and the work done in gravitational are just the same. I know the mass, but I don't know V, which means in this now, I need to make V the subject of the formula, or in most cases, guys, you can just plug and play. That will be 110, a half, multiplied by the mass, which is 0.0030 V squared. This will give you a value. That value can be divided into this. And then by the time you want to get V squared now, V squared you can only get if you take the square root, which is exactly what you see here, what I did to get the square root. You could have seen here to get rid of the half, I would have multiplied both sides by 2. That's why you could see this here. Divided by that 0.03 to give me then an initial speed of 7,300 meters per second. Quite straightforward, guys. The last question for part 1 of motion revision is explain why the speed of the arrow as it hits the target is less than the value. You see now, they said it's less than the value. Why is the speed of the arrow as it hits the target less than the value in B? Now, this is because much of that energy could be lost due to what, guys? And energy is always lost usually due to sound or to heat, or the air resistance was just opposing that from actually moving, which is why the value might be less. And it all stems from where the diagram that you were given. So study your diagrams. With that said, guys, ladies and gents, that was it for part 1 of motion. The next part will now involve pressure and all of those type of things, and just know your formulas. You guys are ready to nail it.